Deep within the walls of a structure so massive it has its own weather system, a quiet revolution is unfolding. This is the Gigafactory, a temple of modern engineering designed for a single, Herculean task: bottling lightning. Today, the world runs on lithium-ion power, but creating these energy cells at scale is one of the most complex manufacturing challenges ever attempted by humanity. We are talking about precision at the scale of atoms, executed across millions of square feet. Inside, over 10,000 synchronized parts work in a dance of sub-millimeter accuracy. To understand the scale, imagine a building that could hold over 100 football fields, all dedicated to moving electrons through solid matter. Every second, thousands of battery cells are born, each one capable of powering a vehicle at 80 miles per hour or keeping a home bright during a storm. But before the energy can flow, we must start with the raw, brutal elements of the Earth. We are going beyond the casing, past the chemistry, and into the very heart of the machine that builds the machine. This is how you bottle lightning.
The journey begins not with wires, but with a dark, viscous sludge known as slurry. In massive, airtight stainless steel vats, active materials are blended with conductive binders. For the cathode, the positive side of the battery, we use a precise cocktail of lithium, nickel, cobalt, and manganese. These powders are finer than industrial flour, with particles measuring only a few micrometers across. On the other side, the anode, we use high-grade graphite, the same material found in a pencil but refined to extreme purity. The mixing process is critical. Even a single speck of dust or a 1% deviation in humidity can ruin an entire batch. These mixers spin with thousands of pounds of torque, ensuring the slurry is perfectly homogeneous, smooth enough to be spread thinner than a human hair. This liquid is the foundation of energy storage. It is the medium through which ions will eventually travel, and its consistency determines whether a battery lasts for 10 years or 10 minutes. The chemistry here is a balance of power and stability, prepared in a vacuum to ensure not a single bubble of air interferes with the coming transformation.
Now, the liquid slurry must become a solid component. This happens on the coating line, a machine hundreds of feet long that operates with the precision of a Swiss watch. Ultra-thin foils of copper for the anode and aluminum for the cathode are unspooled at high speeds. As the foil zips through the machine, high-precision slot dies apply the slurry at a thickness of exactly 100 micrometers. To put that in perspective, that is roughly the width of a single strand of hair. If the coating is too thick, the battery might overheat; too thin, and it won't hold a charge. Automated laser micrometers scan the surface every millisecond, adjusting the flow in real time to maintain a tolerance of less than 1 micron. Once coated, the foil enters a massive drying oven several stories high, where the solvents are evaporated and reclaimed. What emerges is a dry, flexible sheet of active material permanently bonded to its metallic carrier. This is the first time the raw chemicals take on a physical structure, a long, dark ribbon of potential energy ready to be compressed and shaped. To maximize energy density, we must remove every microscopic pocket of air. This is the calendaring process. The coated foils are fed between two massive heated steel rollers. These rollers exert a staggering pressure, often exceeding 100 megapascals. That is like imagining the weight of a professional locomotive concentrated onto the tip of a finger. This pressure crushes the slurry particles together, increasing the material's density and improving electrical conductivity. As the sheet passes through, it becomes thinner, glossier, and much tougher. The rollers must be perfectly cylindrical. Any deviation larger than a fraction of a millimeter would create waves in the foil, leading to catastrophic failure during assembly. We are engineered for perfect flatness. The result is a high-density electrode sheet that can store more electrons in less space. At this stage, the material feels less like a chemical coating and more like a piece of high-tech fabric, dense, metallic, and incredibly smooth. The stage is set for the most delicate part of the operation, the separation. In any battery, the positive and negative sides must never touch. If they do, the energy releases all at once, a short circuit that leads to fire. To prevent this, we introduce the separator. This is a specialized polymer film, so thin it is almost invisible to the naked eye, yet it is one of the most engineered materials in the factory. The separator acts as a gatekeeper. It is porous enough to allow tiny lithium ions to crawl through, but strong enough to block the flow of electrons. Some advanced separators are designed with a thermal shutdown feature. If the cell gets too hot, the pores melt shut, killing the reaction and saving the battery. Within the Gigafactory, these separators are handled in dry rooms, environments where the humidity is kept below 1%.
Why? Because a single drop of water in this environment would react with the lithium to create toxic gas. In this bone-dry silence, the cathode, the anode, and the separator are brought together for the final assembly. The manufacturing of a cylindrical cell, like the famous 2170 or the massive 4680, requires a process called winding. Imagine taking 3 different rolls of wrapping paper and spinning them onto a single tube at blistering speeds. This jelly roll consists of the cathode sheet, the separator, and the anode sheet, all layered precisely. The winding machine must maintain constant tension. Too loose, and the cell will have poor performance. Too tight, and the layers might crack. In a matter of seconds, hundreds of layers are wound into a compact cylinder. This is where the physics of the Gigafactory truly shines. By rolling the electrodes, we create a massive surface area for chemical reactions within a tiny vertical footprint. Once wound, the jelly roll is inserted into a high-strength nickel-plated steel can. A cap is laser welded onto the bottom, and the cell moves towards its first breath of life, the electrolyte injection. This is the moment the dry materials become a functioning electrochemical device. The cell is currently a dry, lifeless husk. To make it come alive, we must add the electrolyte. In a vacuum-sealed chamber, a robotic needle descends with surgical precision, injecting a carefully measured dose of liquid salt solution. This liquid is the superhighway for ions, allowing them to move between the anode and cathode. Because the internal layers are wound so tightly, the liquid doesn't just fill the can, it must be soaked into the materials using vacuum pressure. This process, known as wetting, can take hours or even days. The factory uses advanced vacuum staging to pull the electrolyte into the deepest pores of the electrode sheets. Once the saturation is complete, the cell is sealed with a top cap and a safety vent. This vent is a critical engineering feature, designed to burst at a specific pressure to prevent a cell from exploding if it is ever mistreated. The cell is now physically complete, but it is empty. It has no charge. It is a vessel waiting for its first spark. The most critical stage of battery birth is formation. The newly sealed cells are moved to massive, climate-controlled racks where they are plugged into an electrical grid for the very first time. This isn't just a simple charge, it is a carefully controlled chemical ritual. As the electricity flows in, a solid electrolyte interface, or SEI layer, forms on the anode. Think of it like a protective scab that heals the battery and allows it to function efficiently for years. This process is slow and delicate, lasting up to 20 hours. Technicians monitor the voltage curves with extreme scrutiny. This is also where we identify the infant mortality of cells. If a cell has a microscopic defect, it will reveal itself here through heat or voltage drops. The Gigafactory's formation wing is a sea of glowing lights and cooling fans, thousands of cells breathing in unison, taking their first charge before being sorted by their performance characteristics. Only the strongest survive to move to the next stage, the pack assembly. A single battery cell can power a flashlight, but to move a 2-ton vehicle, we need an army. These cells are now grouped into modules. Robotic arms, moving with a speed that defies their size, pick up individual cells and place them into rigid frames. They are then wire-bonded. A high-speed machine stitches thin aluminum wires from the cell terminals to a common bus bar, essentially creating a massive electrical highway. This happens thousands of times a minute with millimeter accuracy. But there is a challenge: heat. When thousands of cells work together, they get hot. To solve this, thin cooling ribbons or plates are woven between the cells. These plates carry a glycol-based coolant that wisps away heat, ensuring the pack stays at its happy temperature, roughly the same as a human body. This module is the building block of the final battery pack, providing both the structural integrity and the thermal management needed for extreme performance in the real world. At the end of the line, the modules are encased in a high-strength steel armor, creating the large-scale battery pack. This is the final form, a monolithic slab of energy that will become the floor of an electric vehicle or the heart of a city's power grid. Before it leaves the factory, it undergoes a torture test. It is vibrated, tilted, and subjected to high-voltage insulation tests to ensure no current can leak. The complexity we've witnessed is mind-boggling. From raw graphite and lithium powders to a fully integrated power plant, the Gigafactory has transformed the Earth into an engine of the future. This is the pinnacle of human manufacturing, a place where chemistry, physics, and robotics converge to solve the greatest challenge of our time. As the pack is loaded onto a truck, it carries more than just electricity. It carries the results of millions of man-hours and the precise alignment of trillions of atoms. The lightning has been bottled. The future is charged. We are ready to move, and the world will never be the same. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.